Courses in the cement industry. Present to you. To the members of courses in the cement industry. I hope to subscribe to the membership, so that we can continue to provide useful content. In this course we will detailed explanation. All data about the fans. Introduction. Fans are subject to more misuse, abuse, and faulty applications than virtually any other type of equipment. The result of ineffective utilization is high energy cost, which can be reduced to yield sizable savings. The fans provide the motive power to circulate the heating, or cooling medium in most of the systems in use today. In selected applications, specially designed fans are used for materials handling. The control of the energy consumed by fans is very important to the overall efficiency of the system. Definitions for fan. A fan is a device that causes flow of a gaseous fluid by creating a pressure difference on the medium to be transported. The gaseous fluid transported by the fan is most often air, or toxic fumes, whereas blowers may transport a mixture of particulates and air. A brief of the fans. 1. They are the air displacement systems, moving air continuously to moderate pressures. 2. Due to little change in pressure of air in fans, air is considered to be incompressible. 3. They can have pressure rise up to 2 psig. The characteristics of fans can be classified as 1. The volumetric flow rate of the gas displaced by the fan is directly proportional with the fan speed. 2. The static pressure varies with the square of the fan speed. 3. The power consumed varies with the cube of the fan speed. Fan type. 1. Axial fans. It is divided into tube fans, propeller fans, vane fans. 2. Centrifugal fans. It is divided into radial blade, forward curved, backward curved, airfoil. Axial fans. Gas moves parallel to the axis of rotation. There are 3 types of axial fans. 1. Tube axial fans. 2. Propeller axial fans. 3. Vane axial fans. Axial fans. 1. Tube axial fans. The tube axial fans are more efficient than propeller fans, and are capable of higher differential pressures. Tube axial fans have 4 to 8 airfoils or curved blades. The housings are cylindrical tubes formed so that the running clearance between the blade tips and the tube are minimal. The construction results in tube axial fans having higher efficiencies than propeller fans. Ease of installation, reasonable cost, and low maintenance are the main advantages of tube axial fans. They are used in certain industrial applications such as drying ovens, paint spray booths and fume exhaust systems. Tube axial fans are used for wide range of volumes at medium pressure. Where 1. Fans have 4 to 8 airfoils, or curved blades. 2. Running clearance between the blade tips and the tube are minimal. 2. Propeller fans. The propeller type fan, either direct or belt driven, with flat or slightly curved blades, is usually used in places where they operate against very low pressures, and are very seldom connected to a duct system. They are mostly used to move large volumes of ventilation air through large openings in the walls, or roofs where the outlet has a small pressure loss. Briefly. 1. Operate against very low pressure. 2. Move large volumes of ventilation air. 3. Flat or slightly curved blades. 3. Vane axial fans. Other axial fans have blades of an airfoil design, and can be operated against pressure. They are usually direct-driven, and operate at higher speeds than the propeller fans. On this type of fan, the horsepower curve will rise sharply, with an increase in speed or system resistance, so that the motor can be easily overloaded. In vane axial fans there is air guide vane on the discharge side, and the airflow pattern is a straight line, hence improvement in efficiency, and reducement in turbulence is observed. Operate at higher speeds than the propeller fans, the horsepower curve will rise sharply, with an increase in speed and system resistance, so that the motor can be easily overloaded. In this chart, axial fan performance illustrates. Centrifugal fans. 1. Centrifugal fans are made with several blade types, the two main ones being forward curved, and backward inclined. 2. Gas stream moves perpendicular, to the axis of rotation. 3. They are classified as radial blade, forward curved, backward curved and airfoil. Centrifugal fans. Before starting the explanation, we will watch this video together. In this chart, centrifugal fans characteristics illustrates. In this chart, centrifugal fans characteristics illustrates. In this chart, inlet control vanes illustrates. In this chart, inlet control vanes illustrates. Radial blade centrifugal fans. 1. Radial blade fans are used for material handling, and have self-cleaning blades. These are least efficient of the centrifugal fans. 2. They are used for pneumatic transportation, and exhausting process gas in high-resistance systems. 3. With relatively low capacity, they can achieve high static pressure. 4. They can develop high pressures with high speeds. 5. Blades clean themselves. 6. They are not used for ventilating purposes. Forward curved centrifugal fans. 1. Forward curved fans are used in most tow pressure systems, and run at slower speeds than backwardly inclined wheel types. This type of fan at constant speed will show considerable horsepower increase as the system's static pressure decreases, resulting in the possibility of motor overload. 2. They discharge higher volume of air at slower fan speeds. 3. They operate with a moderate amount of noise. 4. They require little space. 5. They are used for clean gases. Backward curved centrifugal fans. 1. The backwardly inclined wheel is used in high-pressure duct system applications, and is non-overloading under normal conditions. This fan will have less blades in the wheel, and they may be flat or slightly curved, in comparison to the closely spaced blades of the forward curved fan, which are never flat. Backwardly inclined fans will have a higher efficiency in their design range, and will usually operate at considerably higher speeds. 2. They develop much of their energy directly as pressure. 3. They develop less velocity heads by operating at medium speeds. 4. Small variations in system volume result in small variations in air pressure. Airfoil centrifugal fans. 1. Airfoil fans have a special backward curved airfoil type blade. These fans have the highest efficiencies, and operate at very high RPM, from 1750 to 3000. They are found on all system types, low, medium and high pressure, but are also the most expensive. 2. They can operate more silently since air forms no turbulence, while flowing through the wheels. In this table, centrifugal fan performance characteristics illustrates. Centrifugal fans. Watch this video together. Impeller. The impeller is normally fabricated from steel plate, and can be either single or double inlet, depending on the duty requirements. Fan would have a forged steel hub, aerofoil-shaped blades and a conical side plate. The impeller would be fabricated stress-relieved then machined, to provide a fine tolerance and surface finish on the hub bore. The inlet ring would also be machined, to ensure a smooth profile, to give good flow at the impeller inlet, and also to provide the required running clearance, between the static suction cones. Impellers can also be supplied, with backward curved plate blades which are more appropriate, when there are higher dust levels present within the gas hot. The plate blade impeller allows a simpler construction, when abrasion protection plates require to be fitted to the blades or center plate.
So here we are looking at the Howden fans. Just dimensionally, the diameter, the outside diameter you're looking at is a 6-foot diameter. The vanes that we're looking at here, they're actually rather like an airplane wing in that they're hollow inside. It's formed then out here on the outside. And I believe there's a total of 11. Oh yes, it's 4 feet wide. 4 feet wide. And one side is more eroded than the other side. One is actually blowing air. The other one is kerosene fumes, as per the client. That's why one side is more eaten up than the other. All the visual. Let's see, let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 11. I'll count again. This I'm a whole 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Actually, there's 10. There's 10 of these vanes for a total of 20. And actually, I have the two rotors stacked up here. But there's a visual. Pretty eaten up. So that's the project. The project at hand is to fabricate two fans as we see them. That's a 13-inch, by the way. That's a the hub. The hub bolts on, and the hub has a tooth-out press fit to the shafts. Shafts are in fairly decent condition. They're straight. Hub mounts here. The fan bolts to the hub. So that's the project. Two fans.
Impeller variation. Many fans within the range have been tested with varying geometry impellers in a standard casing, with variations in blade length and width. Thus each of these fan designs can be considered as possessing a performance envelope rather than a single performance curve. This permits a better optimization during selection. This flexibility therefore has permitted fan development resources to be concentrated on a core range of basic fans, rather than on a larger number of individual designs. Impeller shape. Backward blade fans. This type of centrifugal fan is highly efficient and mechanically robust. Low specific speed fans are characterized by small inlets and long narrow blades. As specific speed increases, the designs become broader, with larger inlets and shorter blades. At high specific speeds, conical side plates may be introduced to assist the air or gas to turn through the impeller. Airfoil blades are used in many high specific speed designs to improve efficiency, as the distance between blades tends to be larger than on fans with smaller inlets. Radial or paddle blade fans are also supplied. These are inferior in performance to backward blade fans, but are inherently strong and have the ability to withstand high dust burdens within the gas stream. Shaft. The shaft is machined from a mild steel forging, and the impeller can be mounted either between bearings, or overhung in the case of a single inlet fan. The shaft is designed to achieve a safe margin between running speed and critical speed. The shaft diameter is dictated by the fan arrangement, the bearing centers and the impeller weight. Up to operating temperatures of 208 degrees C, the impeller is mounted to the shaft using an interference fit. Above this temperature interference fit and a key is used. The size of the interference fit is selected to ensure that the impeller hub bore is kept centrally located on the shaft, under the action of both centrifugally generated stresses within the impeller and thermal expansion. This ensures that there will be no relative movement between impeller and shaft during normal operation. Bearings. Depending upon the duty and the client's specification, the fan can be supplied with either sleeve bearings, oil pressure fed, ring oil or disc lubricated, with or without water cooling, or with rolling element bearings. The located bearing is normally sighted at the drive end. The bearings can be fitted with temperature or vibration detectors. On pressure-fed bearings, the oil lubrication system would normally be supplied with one AC electric pump, and one shaft-driven pump to cover for rundown during a power failure, or alternatively two electric pumps, with a pressurized oil header tank. Fan casing. The fan casing is fabricated from mild steel plate, and is adequately stiffened using rolled steel sections, to be suitable for operation at the design pressure specified. Access doors are provided for inspection and maintenance. The casing will be split with a bolted joint at a suitable position, to allow for impeller and shaft removal. Either a single carbon ring seal, or a floating annular plate seal will be installed, where the shaft penetrates the casing wall. The fan performance is based on a controlled expansion, at a maximum discharge angle of 70 degrees, to a specified area, normally given at the tender stage. This expansion duct is not normally. It is important to note that no unspecified duct loads can be transmitted onto the fan casing, inlet and outlet flange connections, as this can affect the alignment, resulting in changes to the fine running clearances between the impeller and the inlet suction cone. Expansion joints should be fitted. Airflow measurements for fans. The total pressure of an air stream flowing in a duct is the sum of the static pressure exerted on the side walls of the duct, and the velocity pressure of the moving air. In this figure, the illustrated pilot tube is a common device for measuring the velocity pressure. Measurements should be taken in accordance with traverse details shown. The velocity pressure should be calculated for each traverse position, and the readings averaged. Using these measurements, we follow together airflow measurements for fans. The velocity of air in a duct can then be calculated. See this equation. The equation can be simplified for standard conditions of 28 degrees C, and 101.325 kPa, barometric pressure. See this equation. The volume airflow rate can then be calculated. See this equation. Fan performance measurements. The performance of fans is easily determined by calculations based on measured data taken at the fan inlet and outlet using the methods previously described. Several factors, however, can affect the accuracy of the field measurements. 1. Airflow not at right angles to the measurement plane. 2. Non-uniform velocity distribution. 3. Irregular cross-sectional shape of the duct or passageway. 4. Air leaks between the measurement plane and the fan. We follow together fan performance measurements. The total differential pressure across the fan can be calculated from the measured data. See this equation. The total fan static differential pressure can also be calculated. See this equation. The effect of inlet and outlet conditions have not been included in these equations, however they provide a reasonable basis for the further calculation of fan power and static efficiency. Fan performance. Fan power requirement. The work done by a fan can be measured by the quantity of air it delivers, and the pressure against which this air is delivered. Assuming the fan is 100% efficient, the theoretical power, W, required to move a given volume of air, Q, against a total pressure, P, can be calculated as follows. See this equation. The overall fan efficiency relates the theoretical output against the electrical power supplied to the fan system, and includes fan losses, belt drive losses and motor losses. Note that the efficiency stated by most fan manufacturers is for the fan unit alone, the theoretical output as a ratio of the power input to the fan shaft. Fan performance. Fan performance curves. Fan performance information is available from the manufacturers on all production fans in the form of fan performance curves. This figure shows a typical curve. We follow together, fan performance curves. A fan operates along a performance given by the manufacturer for a particular fan speed. The fan performance chart shows performance curves for a series of fan speeds. At fan speed N1, the fan will operate along the N1 performance curve as shown in the schematic. The fan's actual operating point on this curve will depend on the system's performance characteristics. We follow together, fan performance curves. In any fan system, the resistance to airflow, pressure, increases when the flow of air is increased. The pressure required by a system over a range of flows can be determined and a system performance curve can be developed, shown as SC1. This system curve can then be plotted on the fan curve, to show the fan's actual operating point A, where the two curves N1 and SC1 intersect. This operating point is at airflow Q1, delivered against pressure P1. We follow together, fan performance curves. Two methods can be used to reduce airflow. One is to restrict the airflow by partially closing a damper in the system. This action causes a new system performance curve, SC2, where the required pressure is greater for any given airflow. The fan will now operate at point B, to provide the reduced airflow Q1, against pressure P2. We follow together, fan performance curves. The airflow could also be decreased, by leaving the damper fully open, and reducing the fan speed N. The fan would operate at C, to provide the same Q, airflow but at a lower pressure P. Reducing the fan speed is a much more efficient method, to decrease airflow since less power is required, and less energy is consumed. Fan laws. The fans operate under a predictable set of laws concerning speed, horsepower, and pressure. A change in RPM of any fan will predictably change the pressure rise, and horsepower necessary to operate it at the new RPM. If only the RPM is changed, the following will take place. In this figure illustrate 1. Air volume in cubic meters per second, will vary directly as the revolutions per minute RPM. 2. Varying the RPM by 10% decreases, or increases air delivery 10%. See this equation. We follow together fan laws. In this figure illustrate 1. Static pressure, SP, will vary as the square of the RPM. 2. Varying the RPM by 10% decreases, or increases the static pressure by 19%. See this equation. In this figure illustrate 1. Fan power, kilowatt, will vary as the cube of the RPM. 2. Varying the RPM by 10% decreases, or increases the power requirement by 27%. See this equation. Fan accessories. 1. Access doors. Bolted and quick opening access doors are available for easy access to the fan interior for inspection or cleaning. All access doors are gasketed, and are constructed with either evenly spaced studs, or heavy-duty hinges and handle-type nuts, which require no tools to open. Raised bolted access doors are available for use, where insulation is being applied to the outside of the fan. 2. Inlet bell. On installations with an open inlet, no duct work at the inlet of the fan, a streamlining inlet bell is required to achieve the catalog performance. See this video. 3. Outlet dampers. Due to the performance characteristics of industrial fans, a damper on the outlet of the fan is a very efficient way to control volume. An outlet damper can be used to reduce the power consumption of a fan operating at high temperatures, or a fan operating in low-density gas streams. During a cold startup, the outlet damper begins in a closed position, and is opened gradually as the fan reaches operating temperature. This allows for the use of a smaller motor sufficient to handle the duty at higher temperatures. See this video. Four. Inlet vanes. For reduced flow situations with relatively clean air, inlet vane type dampers are available to maintain fan efficiency. The inlet vanes are external type, attached to the inlet of the fan. Standard construction inlet vanes are suitable in applications up to SUD. High temperature inlet vanes are also available for temperatures up to 300 degrees C. 5. Inlet boxes. An inlet box is designed to minimize pressure drop and airflow losses. Inlet boxes are recommended for applications where uniform flow is difficult to obtain due to limited space, or where the air must enter the fan at an angle. Inlet boxes can be either detachable or integral to the fan. This option is available with an inlet box damper to provide increased airflow control. See this video. Six. Shaft coolers. Where high temperatures are encountered, the aluminum shaft cooler is recommended for dissipating heat and protecting bearings from the high temperature atmosphere. See this video. Seven. Shaft seals. The standard shaft seal is a non-asbestos type, sandwiched between two plates and the fan housing, providing a seal for most materials being handled. A variety of special seals, including mechanical type stuffing boxes, is available for gas-tight applications requiring more positive protection. See this video. Eight. Drains. A pipe coupling can be welded to the lowest point in the housing, scroll low allow wash water, or condensation to drain. 9. Spark-resistant construction. 3 fan constructions are available for spark resistance. The materials used in the construction of these fans minimize the potential of sparks being generated by striking or rubbing components within the air streams. Notes: 1. The user must electrically ground the fan. 2. Standard spark-resistant alloy is aluminum. 3. Bearings must not be placed in the air or gas stream. Thanks for following the channel, Courses in the Cement Industry. And please help us to continue and provide more information by subscribe to the membership and inviting your colleagues to watch this channel.